In 5.5, we're going to talk about the derivatives of inverse trig functions, and we're going to define what those derivatives are. So we're going to start by proving 3 of those derivatives, and then we're going to use the fact that they have the same structure to come up with the other 3. So we're going to start by looking at the derivative with respect to x of arc sine of x or sine inverse of x. So thinking through this first, let's write this in a way that's maybe a little bit easier to work with. So let's think about this as y equals inverse sine of x. Now, we don't know how to do anything with derivatives with inverse functions, but what we do know is that we could manipulate this equation to put it just to be in terms of sine, which is something that we do know how to differentiate. So we could actually use properties of trig to say that this is the same thing as x equals sine of y. And we do know how to manipulate sine of y. We could take, implicitly, we could differentiate both sides. This would give us that 1 equals the derivative of sine is cosine of y dy dx. Now, if I wanted to manipulate this to solve for dy dx, I would get that dy dx is equal to 1 over cosine of y. Now, I was originally looking for the derivative with respect to x, so I probably don't want to leave this in terms of y. I probably don't want to leave this as 1 over cosine of y. I want to find a way to relate this back to something that I know to put it back in terms of x. So I'm going to draw a right triangle here, and I'm going to think about where we started. We started with the fact that sine of y, so if I put y here, sine of y is equal to x. So I could call this x, and I could call this 1. And then I could use the Pythagorean theorem to solve for this missing side to get 1 minus x squared. So now I'm looking for 1 over cosine of y, which is exactly the same thing as secant of y, and secant of y would be adjacent over hypotenuse. Sorry, would be hypotenuse over adjacent. Cosine of y would be adjacent over hypotenuse. Secant of y, so this is equal to secant of y, and secant of y is equal to hypotenuse over adjacent, 1 minus x squared. So I'm using this triangle to tie things back to being in terms of x because this original problem was asking us about the derivative of arc sine or inverse sine of x. So that is how we get here. And you'll notice that this version down here that I just put a box around has the u prime in the numerator in case there is a function happening within the sine of x. Now let's similarly look at arc secant. So I'm going to go ahead and delete this triangle in blue here. So pause the video if you want to make sure you have that down. So I have some more space for arc secant. All right, let's start by saying y equals inverse secant or arc secant of x. And then just like we did on the last one, let's do some rearranging. And let's use properties of trig so that we can say that x is equal to secant of y. Now we can take the derivative with respect to x of both sides. That's going to give me 1 equals the derivative of secant of y is secant y tangent y times dy dx because we are differentiating implicitly. So we can solve for dy dx. That's going to give us that dy dx equals secant y tangent y. And again, we're in a similar issue here, or we have a similar issue here in which we need to get these out of y's and turn them into x's. So let's go ahead and draw our triangle and see what we can figure out. If secant of y is equal to x, that means hypotenuse over adjacent is equal to x, which means now I can use, again, the Pythagorean theorem to find this missing side, which is going to be x squared minus 1. The square root of x squared minus 1. And shame on me, this should be 1 over secant y tangent y. When I divide it on both sides, it goes into the denominator. All right, now let's try and manipulate this 1 over secant y tangent y to get it back in terms of x's. Well, we already know from the very beginning of this problem that secant of y is equal to x. We also know, based on our triangle, that tangent of y opposite over adjacent is just going to be, this, based on this triangle, the square root of x squared minus 1. Now we have some domain issues that we need to account for, and something to note is that secant y tangent y is always going to be positive because secant and tangent are always going to be the same sign over their domain. And if they're always going to be the same sign over their domain, when I multiply two negatives or two positives, I'm going to end up with a positive number. But the only way to make sure that that stays true in our derivative is to put absolute value around our x. So this makes sure that we don't have any domain issues. Since secant y, tangent y should always be positive, I can just throw absolute value around x to make sure that I know that this should always be positive as well. So you can see that derivative worked out down here. And again, this is in the chain rule form with the u prime in the numerator. All right, why don't you pause the video and go ahead and try and work through arctan on your own. All right, so just like with the other two, we're going to start with y equaling inverse tangent of x, which means that x equals tangent of y. We're doing this so that we can then differentiate both sides with respect to x. That's going to give us 1 equals the derivative of tangent is secant squared y dy dx. So dy dx equals 1 over secant squared of y. Again, I'm going to set up my triangle to see what's going on here. Let's make that actually look like a right triangle. There we go. So we started with x equals tangent of y. So the tangent of y is opposite over adjacent. That's going to be x over 1. That means that this is going to be the square root of 1 minus x squared. I'm sorry, not 1 minus, 1 plus x squared. The square root of 1 plus x squared, right? X squared plus 1 squared equals the hypotenuse squared. So the hypotenuse is going to equal the square root of 1 plus x squared. So secant is hypotenuse over adjacent. Or we could say that secant squared, this is the same thing as cosine squared of y. And cosine is going to be opposite over adjacent. So dy dx is going to be 1 over the square root of 1 plus x squared, quantity squared, which is going to give us 1 over 1 plus x squared. So that is going to come into play right here for tangent. We could do the same process for the cofunctions. We definitely don't need to because they have the same structure except they are multiplied by -1. So you'll see that in the lower three functions. So these inverse trig derivatives, you should know these. You could derive them if you really needed to. That's exactly what you should do if you get stuck on a problem involving them. But it is probably better for you to be able to not have to derive them every time you're using them. So let's look at some examples in which we are finding these derivatives. All right, on number 1, the first thing I'm going to just point out, and again, some of you don't need me to point this out for you, but is that u in this case is equal to 2x, which means that the derivative of the inside is going to be equal to 2. And that's going to come into play in the numerator if you look back at those boxes that we created for these derivatives. So the derivative of arc sine is 1 over the square root of 1 minus 2x, in this case, quantity squared. And we're going to multiply that by the derivative of the inside of the function, which is 2. So this is going to become 2 over the square root of 1 minus 4x squared. Similarly, on number 2, u is equal to 3x, so du is equal to 3. So there's going to be a 3 in our numerator. And we're going to deal with arctan in the same way that we did on the last problem, except for tangent instead. So arctan is 1 over 1 plus 3x, in this case, quantity squared, times 3. So this is going to become 3 over 1 plus 9x squared. Why don't you go ahead and pause the video and work through the rest of these, and then unpause the video and see how you did. So on number 3, dy dx is going to be -1 over 1 minus the square root of x squared. The square root of 1 minus the square root of x squared, times the derivative of the inside, which is 1/2 x to the -1/2 power. So that can be simplified to -x to the -1/2 power over 2 times the square root of the quantity 1 minus x. On number 4, u is e to the 2x, so du is 2e to the 2x. That's going to be in our numerator. In our denominator, the absolute value of e to the 2x times the square root of e to the 4x, or e to the 2x quantity squared, minus 1. Now, something to note, you could leave it like this. However, e is always going to be positive, so having the absolute value here is a little bit redundant. And if you were able to get rid of that absolute value, you could actually get rid of that whole term and just have 2 over the square root of e to the 4x minus 1. So just important things to notice to help you simplify a little bit further. On number 5, we're going to use the chain rule. So we're going to take the derivative, so chain rule. We're going to take the derivative of the outside. So the derivative of regular tangent is secant squared, evaluated at what's already in there. So evaluated at arc sine. Multiplying that by the derivative of arc sine, which is just 1 over, I'm running out of space, so I'm going to make this fit here, 1 over the square root of 1 minus x squared. So this is really just going to be secant squared arc sine of x over the square root of 1 minus x squared. On number 6, we're going to be using the product rule. So dy dx is going to equal, the derivative of x is x, so arctan of x plus x times the derivative of arctan, and the derivative of arctan is just 1 plus x squared. On number 7, our u on the inside is going to be x squared minus 1. Again, you don't have to set it up this way. I just want you to see. So then du is going to be 2x dx. So this is going to be, let's use blue, dy dx is going to equal this derivative we just found, 2x. According to arc cosine, it's going to be negative over the square root of 1 minus the quantity x squared minus 1 squared. And you could simplify that. You could make that negative 2x over the square root of what you get when you expand that out, but that just seems a little unnecessary right now. It's going to save us time and effort to just leave it like this, negative 2x over that radical. And then number 8, we are just adding together 2 different derivatives here. Let's use black. So y dy dx, you know what, let's go down lower. Dy dx is going to equal, well, the derivative of arc cosine is negative 1 over the square root of 1 minus x squared. The derivative of arc sine is 1 over the square root of 1 minus x squared. So when I add these together, I'm just going to get 0. All right, very last question, and this is a calculator question. We're going to find increasing, decreasing, concavity intervals, points of inflections, and relative extrema. So let's first find our derivative, our first derivative. We're given our second derivative. So our first derivative, because the chain rule is going to be 2 times arc tangent of x times the derivative of arc tangent of x, which is 1 plus x squared. Our only critical number here is going to occur when x is equal to 0. If we make a sine chart, that's going to give us negative positive for our derivative, which means there is a relative min at 0, 0, since f prime changes from negative to positive there. It is decreasing from negative infinity to 0 and increasing from 0 to infinity. And then you can use your calculator to find out when this is 0, so this you're doing on your calculator. You're going to get that your possible points of inflection are when x is equal to plus or minus 0.765, negative 0.765. Oh, I am definitely going to run out of room here, so I might just tell you some of these things. This is going to be negative, positive, negative. So we are concave down. Let's see if I can fit this. Concave down from negative infinity to negative 0.765 and from 0.765 to infinity. We are concave up, and that's true because the derivative is negative. We are concave up between negative 0.765 and 0.765, and that is true because the derivative is, or the second derivative is positive, which means we have points of inflection, or inflection points, at plus or minus 0.765, comma 0.426, because the second derivative is changing sign. So I didn't justify everything very well here. I was very much out of space. So important things to remember. You should know these derivatives here. You should know these inverse trig or arc trig derivatives. You should be able to derive them if you're stuck. I'm not going to be explicitly assessing you on the derivations, but you should know how to do them if you get stuck, and you should be able to know how to use them to manipulate different problems. Looking forward to supporting you in class. Thanks for listening.